Actually, sorry. Maybe I'm muting myself. Did you hear me earlier? Hi, Jeongwan. You're a co-host now. And please feel free to test the screen sharing if you want.
Oh, hi, Juvin.
Hey, hi. I was talking to myself. I was muting myself earlier. So sorry for that. Do you need more than one device, or you are just using the same one you are speaking now?
More than one device? Oh, no, yeah.
In case you want to, in case I need to add another device as co-host, let me know. Otherwise,
no,
let's go ahead and share.
Yeah. That's fine. Maybe I can share my screen.
Yes, please do. Just interrupt that and go ahead.
Yeah. Okay. Do you see my
yes,
my screen?
Thank you. Yes.
And it worked? Do you see my scribble? Okay, great.
Yes, great. So we will start maybe 2:30-ish, and you'll have at least 90 minutes. If you wanna go earlier, or go overtime, it's not a problem.
Right. We have plenty of time, I guess.
Yeah.
Oh, I didn't turn on my video. Yeah.
How is life? How are you doing? Good. Yeah, maybe we should start. Okay, welcome everyone. Welcome to Harvard CMSA Quantum Math and Physics Seminar Series. It's our great honor to have Jeongwan Haah from Microsoft Quantum to tell us some of the very fundamental problems that he recently thinking about. It's a degeneracy bound for homogeneous topological order. I would like to remind the audience, please feel free to interrupt and interact with Jeongwan and ask questions. So Jeongwan, it's all yours. So please. 감사합니다.
Thank you.
Yeah.
Thank you, Jeongwan. So I should resume share. Yeah. Can you see my screen?
Yes.
Okay, great. Yeah. Yeah, as always in this online talk, more interruption, the better. So let me start with well, what problem I want to address. So there are many examples of topological states in literature, and most of them look that they are homogeneous, but I want to consider some mathematical criteria when we can say homogeneity. The first criteria or condition that easily come to mind would be some translation invariance. If you have a lattice and if your Hamiltonian is described by some finite data that is repeated over the lattice, then, well, that sounds like a homogeneous condition. This may lack isotropy. The rotation invariance might be broken, but at least along the spatial translation invariance, homogeneity is obtained. Anything that any mathematical framework or topological quantum field theory as a functor from some topological objects down to some algebraic objects. Typically, it is a space-time manifold, and the target is some categorical structure. In that setting, this underlying state is supposed to be homogeneous, and it is more than that. In that it tries to capture many states on a different manifolds and bundle them up to say that, oh, this family, this functor is describing something homogeneous. Another attempt that comes to mind is that, oh, we should consider a sequence of states parameterized by some lattice overall system size, say the smallest system defined on some 10 lattice spacing, say. These are all finite systems, but we can consider a sequence of such as states. And well, in this picture, these two states must be related somehow. Otherwise, the collection would be meaningless. And the one concrete relation in this picture is that, oh, there must be some unitary that consists of local gates and some expansion of the space so that we can map one state into another. This notion is particularly propelled from Jeongwan Haah under the name of liquid states. But this is not completely satisfactory because of the fractals. So let me just briefly tell you what the fractals are. Well, this is a
something.
Sure.
Sorry, are you audio say TI? What does that stand for? Just make sure. TI means.
Oh, translation invariance.
11. Okay. Thank you. No problem.
So the fractals, well, it is started with a simple lattice model, an example that is translation invariance defined as some cubic lattice with a strictly finite interaction with an exactly solvable energy spectrum. But it doesn't, well, it obeys the translation invariance at least, but it does not satisfy any axioms of the topological quantum field theory. And even the RG picture doesn't really fit in the sense that if you were to disentangle or apply certain shallow quantum circuit on the ground state of some particular Hamiltonian, then at a lattice of 2L sites in the linear dimension actually becomes 2 copies of itself. So there is some bifurcating phenomena is observed in the entanglement renormalization proof flow. But translation invariance is somewhat inconsistent with the TQFT picture that one could believe that, oh, any topological theory should follow, because, well, not every manifold admits a translation group action. The torus, if you impose a periodic boundary condition, then it becomes the underlying manifold becomes a torus. There, it is obvious that we have a group action, which we interpret as a translation. But what about sphere? Well, you get some rotation, but there's a fixed point. Why is it translation? Or any higher genus manifolds, it's unclear how to define the translation. The situation becomes even worse, well, only worse in higher dimensions. So translation invariance and TQFT, they are somewhat, they intersect, but not include one another. So, well, yeah, I promised to tell you what fractals are, just for your background. It is a lattice model with a gap above energy gap above the ground state subspace, but the excitations behave in a somewhat weird way. There is a localized excitation that is allowed in the theory. You can insert such a localized excitation by some infinitely supported operator. However, there's no local operator that moves this particle to another location. They are stuck in the location, and their motion is prohibited energetically. And perhaps most weird phenomena in the fracton is that the ground state degeneracy, although it is gapped and they are locally indistinguishable, meaning that if you give me a local operator acting on a ground state subspace, then as long as it is local, it does not give you any information about what particular ground state you are in. If the pi denotes the projector onto the ground state subspace, then any local operator O conjugated by pi results in some scalar action depending on the operator itself, but that scalar action is uniform across all the states in the ground state subspace. However, the number of such states in the ground state, the degeneracy of the ground state can be a very sensitive function on the system size. For the special case of so-called cubic code, the number 1 cubic code, the ground state degeneracy follows this formula. The log of the ground state degeneracy has some number theoretic dependence on the system size. You take these polynomials and take GCD and read off the degree. And for special cases of system sizes, this is lattice model, so we can talk about the precise number. And if the system size, linear system size is a power of 2, then it becomes sub-extensive. The log of ground state degeneracy is proportional to the linear system size, or it drops to some constant number if it is just one lattice spacing larger. So such a behavior is a caricature of the fracton phases. I'm not trying to define what the fractons are. I'm just exhibiting a particular example, some property of the fractons. But in all, the one important thing I want to remark in any of the discussion regarding the fracton physics is that because of the local indistinguishability, the bulk wave function, if you look at the ground state wave function from the bulk without touching the boundary, then it's completely normal. Regardless of the boundary condition, they live exactly the same for the local observable. therefore, thermodynamic limit as a functional from the algebra of local operators down to a complex number, that's well defined. So thermodynamic exists, and people now wondering how we should capture this in a more broad terms. Could there be some TQFT-like description? Does there always exist some bifurcating or with many branches, entanglement RG and so on? Meanwhile, last year, maybe 2 years ago, it's approaching, some very general construction is provided, and it comes under the name of topological defect network, and it is developed by these authors. And the basic idea is that you can describe many examples of the fractal models in the following way. You prepare small blocks of the conventional three-dimensional topological order. It can be gauge theory or some weird versions of it, or even anomalous ones. And then you juxtapose those blocks in a certain way, and you connect those blocks by some strong interaction, by filling their boundary and the boundary of the boundary and so on. So you have a hierarchy of, they call it strata, how to glue those blocks together. Starting from the 3D block, you glue the two-dimensional boundary, and you fill in the one-dimensional codimension 2 void, and you finish with the zero-dimensional cells. And you end up with some system with the larger system size. And the construction tells us that, oh, there are at least 2 length scales. The beginning block, there's one block, is supposed to be some conventional topological state. So it has some lattice spacing, the UV cutoff, and each block comes with some large enough that we can talk about topological phase. And then you glue them together to obtain an even larger system that is capital L. So we have length scales hierarchy, something like this. Now, how should I think of a phase in this construction? Should I take this as a constant or this as a constant? I mean, the ratio between capital N and L can be taken as a constant, or the ratio between small a and the little l to be constant. Or you can interpolate between any choice between the two. Like I could choose the small l to be capital L to the, say, 1/3 or something. Of course, this is arbitrary choice number. There is no meaning to it. So in this construction, it becomes a real challenging question. When can we say the resulting state is homogeneous? That's the motivating question for me. And on the other hand, all the known examples for the fractal phase, they obey this universal law of the law of degeneracy. The log of the ground state degeneracy is not the volume, so it's sub-extensive. However, it is some growing function, and growing function is upper bounded by the linear system size raised to the power, some integer power, where the integer is the space dimension minus 2. The small d represents space dimension. There's no time here. Yeah, some codimension 2 thing. Is this always universal? Is this really universal? Is there any example that goes beyond this number? Well, if you just impose the local indistinguishability, put differently, if you demand that the ground states are indistinguishable, the reduced density matrices are all the same for any local region. If you demand just that, then it is conceivable that, oh, maybe we cannot have the truly extensive ground state degeneracy, but anything that's sub-extensive may be allowed. So you may wonder that the log of ground state degeneracy grows as fast as some linear dimension raised to the power, that is, as long as it is smaller than the space dimension. Maybe it is allowed. yeah, we cannot rule it out. And I want to address this question, and under a reasonable assumption of homogeneity, this bound is actually the best. You cannot improve it because there is a saturating example, and all instances of a certain condition that I'm going to talk about is going to obey this law. The ground state degeneracy can only grow as a codimension 2 volume. If you
Excuse me.
Yes.
The detail D is the spatial dimensional space-time?
D is space. D
Space.
is always space, yeah.
Okay. So how about, can we test one example in one-dimensional space, one-dimensional time? We don't have topological order, but that will let statement.
Right. So if you plug in D equals 1, then this is a decreasing function in the system size. So you end up with the log of degeneracy is approaching 0, meaning ground state degeneracy is 1, which is consistent with all the knowledge that in 1 dimensions we don't have topological degeneracy. Starting with 2, space dimension 2, you may have some constant degeneracy. In 3 dimensions, you may have some growing function.
Okay, fine. Thank you.
Yeah. Okay, so I want to introduce a notion that I call it homogeneous topological order. One can debate whether the name homogeneous is appropriate, but I will defer that discussion later. It's just name. So what's my notion? The notion is not about Hamiltonian. It has nothing to do with the Hamiltonian that I want to emphasize. It is a condition on the ground state subspace projector. I say ground state, but since there's no Hamiltonian, it can be any subspace actually. It's just a notion on the subspace in your Hilbert space, which we can just call it ground state subspace. And I will denote that the projector onto that subspace as pi. And then I will consider a system of discrete degrees of freedom. It's not a continuum field theory. It's still a lattice model. But to be concrete, I always want to impose that if you give me a point, and if I consider a unit ball around it, unit ball whose radius is my lattice spacing, say A, and then in that ball, if you collect all the degrees of freedom and take the dimension of that local Hilbert space, then that should be a sum constant. It's a reasonable assumption. You cannot have too dense location. Here I have a lot of degrees of freedom, and there are too sparse. Well, I don't allow that. It should be uniform. The dimension density must be some constant, independent of anything else. And I will consider operators that act within my ground state subspace. Again, I say ground state, but it's an arbitrary subspace. So by acting within, I literally meant this just to commutativity. An operator T should commute with the ground state projector pi. And since we are restricting we are only interested in the action of the operator that acts within some subspace, the very operator is not relevant to us too much. There can be some other operator, say T prime, whose action on my pi could be the same. The difference restricted to pi could be just vanishing number. In that case, I just say that 2 operators are equivalent for obvious reasons, right? They act in the same way, so they are equivalent. So now here comes the condition. So far, everything was just a convention, I should say. So pick an arbitrary subset S in your lattice. It is a collection of quantum spins in your lattice. There's no notion of continuity or whatsoever. It's just some subset of qubits. And then you take a small a neighborhood of that set. So my space here my space comes with a metric. So you can imagine the Riemannian manifold, of course. And according to that metric, I take a neighborhood of my qubits. So if my system was, say, on this picture, then if you give me, if my S, the set of qubits, is like distributed along like this, it consists of 6 qubits, then a neighborhood is going to be this and this much. Okay, that's my a neighborhood. Then the condition, well, the assumption is that if you take such a neighborhood, then it should be a collection of disjoint union of topological balls. So, well, this example is a valid example for the first 2 conditions. But if I chose like these qubits, and if I take a neighborhood of it, then it will be something like this. And this is not a disjoint union of topological balls. It contains, well, if there's a periodic boundary condition, say, that it contains an essential cycle. So this set of points I do not consider. Okay. Now, if that's the case, then, then for any operator that acts within the ground state, there should be an equivalent operator whose action on the ground space is the same, such that the support of the equivalent operator T prime should not touch anything in the A neighborhood of S. So it is a bit of a mouthful condition, but intuitively, what's going on is this. You give me some region, some subregion on the torus, say, that is a topologically disjoint union of balls, disks. Then, whenever I introduce some transformation on the ground space, I should be able to find a representative of the same action that avoids these regions. Yeah. Even if if the chosen T was passing through my chosen set of balls, then I should be able to, this is my condition, I should be able to find an equivalent operator that just goes around it. Okay, is the notion clear? Okay, I assume so. Now, let me
as long as the region that the chosen does not span some non-trivial cycle in a large volume, you certainly can do that.
Yeah, well,
yeah, as long as there's but I don't see obstruction, so that's why I think there's no issue.
You don't see obstruction. Oh yeah, well, I will give you examples and non-examples later, so stay tuned. Okay, so let me remind you with the connection to the local indistinguishability. And this is a tool developed from some information theory. So I'll just state the result, not going through any deeper discussion. So all these conditions are equivalent. When I say equivalent, it doesn't mean that any of them are true, and any of them is true. But whenever one is true, then the other 2 is true. Okay. So the condition is this. The first one is probably most familiar. For any region.
Sorry, can I ask a question?
Sure.
Is there a restriction on how close the balls should be to each other? Otherwise,
no.
But can we not then cover uniformly the whole manifolds with balls that are almost touching each other?
So okay, right. So you came to a right point. So, the taking a neighborhood actually takes care of that worry. If I didn't take a neighborhood, then this condition is vacuous. Vacuous in the sense that the first condition, first two, 1 and 2, these two are always satisfied. Since my system is discrete, S can be the system itself, and well, those points is a collection of topological balls. So then the third condition cannot ever be satisfied, because you have operators should be supported somewhere, and you just demanded that it should be supported nowhere. So that's a vacuous notion, and that's why I am taking the A neighborhood, and that by tuning that A value, you can avoid your worrisome or vacuous case. You could, of course, cover most of your space by disjoint union of topological balls. You can do that. But if I demand the same condition with a slightly larger A, then this situation is avoided, because with a slightly larger A, your packing open balls would cover everything.
I see. Yeah, thank you.
Yeah. So what I introduced is directly a variant. Well, yeah, it is just that the third condition for any logical U. Well, logical is a technical jargon that is used in the information community, just to say that, oh, the operator commutes with the subspace projector. Yeah, the subspace projector commutes with that. Then there exists an operator supported on the complement of the support of U. So the A can be avoided such that the action on the subspace are the same. This is my condition. Well, and the equivalent conditions are that, let me just mention this. So this is a mutual information between your avoided region and some reference region. So in the information theory, what you always do is there's a target state living in some other space, and you bring a reference system that comes out of nowhere, but which can be entangled with your system. You always think of this situation for technical reasons. And when you do that, for arbitrary entangled state between your system and a reference system, the mutual information between the region you are considering and the reference must always be 0, regardless of what state you chose. That's the decoupling condition. And the first one is probably the most familiar to you, that for any local operator, for any operator supported on A, the conjugated operator acts on the ground state subspace by some scalar action in a uniform way. So all these conditions are the same. The reason I chose to phrase my condition in this way comes in the approximate setting, which I will discuss later. But I just want to say that the usual notion that comes in the local indistinguishability is actually the same thing as my notion that you can avoid the regions as long as they are ball-like. Okay, so before going to the main claim that under this assumption the degeneracy is bounded in that way, let me remark how general my notion is. Well, as Jeongwan said, that in any conventional topological order, my notion is true, because there, whatever manifold you give me, the operators acting on that and acting on the ground state subspace is going to be some self-manifold, or supported on some self-manifold. And the precise location of that self-manifold is never important. Only the topological homotopy class of that is important. And that means whatever disjoint balls you give me, I can always avoid that balls. A string operator can go around any ball, surface operator can go around that any given ball. Well, this is true for any subdimensional operator. So that's easy. Another intuitive picture is that whatever topological theory you may imagine, if you start with a vacuum, a ground state, and then you hit the system with some operator, then that will create certain excitations. But since you have created those excitations by a local operator here, you should be able to fuse them to vacuum again. What does that mean? So I started with the vacuum, created it, and then by pushing the particles toward the center of my region, I go back to my vacuum. And the overall process is like a correction procedure. The damaged state is like corruption of my in the information theoretical language is my encoded information, and going back to vacuum is like the recovery of that. And being able to recover the vacuum amounts to say that my damaged region was correctable, and that correctability actually is equivalent to my notion. And this picture continues to hold not only for any conventional topological theories, but for fraction phases too. The individual particles are immobile. However, if you are willing to pay some energy price, then they can be fused to the vacuum, as long as they were created by a local operator. And my notion continues to hold for any basically any short-range correlated Hamiltonians with the local indistinguishability. The difference is that here, T is some operator that is supported in a ball. That's the usual setting where people do not consider an operator that are far apart here. But because we are considering as long as we consider short-range correlated states, then this patch and that patch, they don't have any correlation function that is non-zero. So if you demand this local indistinguishability for only those individual patches, then any collection of it is also correctable. So that's fine. So I think I argued that my notion is reasonably general. And let me give you a non-example to enhance our understanding of the notion. So it's like the defect network construction. I started with the conventional patch that has a length scale small l. There's a tiny, not a spacing scale, but I didn't draw that. Here's an intermediate scale length, a small l. There's a truly macroscopic length scale, capital L. Now let's try not to glue any of those. Just a juxtaposition of small blocks. It's a very boring system, but let's consider that as a non-example. And I suppose I chose certain boundary conditions for those blocks such that individual block has some degeneracy in it. Well, certainly I could do that. And then the degeneracy of the full system is going to be the product of all of them, which is a very large number. And in this setting, it will grow fast. It could grow faster than the codimension 2 volume. And this system fails to satisfy my notion. Okay, what's the counterexample? So my choice of subset is, say, this block, and that block. I have chosen 3 blocks. And then I chose the A neighborhood. Well, it happens to enclose exactly those 3 blocks. And then my condition demands that, oh, this collection of 3 balls should be correctable. But I started with the block that has some operator in it. I mean, it has some degeneracy in it. So there exists some operator that is supported in this ball that distinguishes the ground state. So they're not correctable. If you lost one block, then there's no way to recover to the original vacuum state. the key is that when I demand my correctability, I did not impose any condition on the length scale of my balls. Now, let me go back to notion once again. S is arbitrary. While taking a neighborhood, that does not increase any size of S significantly. And I only demand the topology of that a neighborhood to be just topological balls. There's no length scale involved. And I demand that those collection of balls should be correctable. Here, there were intermediate length scale, and which could be very smaller than my overall system size. So my topological ball could be larger than this intermediate length scale. And this example fails to meet my criteria. So according to me, this is not inhomogeneous. Okay, now let's look at the mathematical consequence of my notion. And the results are the following. So let's start with the most general case. The log of the degeneracy, the dimension of pi, is upper bounded by some constant that depends on the isometry class up to overall scaling. So this is purely geometry of the underlying manifold dependent constant. And of course, there's another constant depending on the dimension density. We call that for any given ball of radius r, there are some bounded, constant dimensional local Hilbert space assigned. So those two constants are natural. There's an interesting piece that says the diameter of the system, here diameter for any Riemannian manifold is defined to be the supremum of distance between any 2 points, supremum taken over a pairs of states. Yeah, this is diameter. Diameter divided by the lattice length scale, so it is the dimensionless quantity, raised to the power d minus 2. So the minus 2 is the key. This is the general bound. You can specialize to say something more. When it comes to 2 dimensions, then, well, the general bounds has no diameter dependent term, but you still have the density of dimension density coefficient. But interesting piece is that there's another constant that depends only on the genus. So even if I started with the Riemannian manifold, Riemannian surface, I end up encoding only the topological data, not the geometry data. It's just a genus and the local quantity. That's it. Nothing else. Even if you make a system larger, there's no log correction or anything, just that. And if you consider a d-dimensional sphere, a very special standard sphere, the d-dimensional sphere, then the larger than 2. No, actually, no, you don't need that. Yeah, d-dimensional sphere. Then your ground state degeneracy is actually 1. They are non-degenerate. You cannot have an even constant number of them. You may want to recall the disk axiom of the modular tensor category. This is a physical phrasing of that. Any question on the statements?
Yes, question. What is the first statement on this isometry class? Maybe you explain. Yeah. I didn't get. And the second question is that how about when the spatial dimension is 1? Do you also get some statement? Is that just again a single ground state or something? Thanks. Yeah, 2 questions. Thanks.
Yeah. Or right. Yes. Or d equals 1. D equals 1. We only have a line or a circle because we are focusing on manifolds. So in both cases, they're all 1. So isometry class. Okay. So what is isometry? If you have 2 Riemannian spaces M and M prime, then isometry is by definition some diffeomorphism between M and M prime, such that it preserves the metric. So any 2 points X and Y, if you map it phi of x and phi of y, then their distance is the same as this distance. Well, distance, of course, is measured according to metric of m. Here, according to the m prime. So as a Riemannian manifold, they are just identical. You cannot distinguish them. Yeah, Taran has a question.
Yeah, hi, I have a question.
Hi.
So is it, so here are you assuming that your manifold has no boundaries?
No, it doesn't matter. It may have boundary. Yeah.
So if I consider 1D system with, let's say, the Kitaev chain, so it has 2 Marana n nodes at each edge. So the ground state degeneracy is true then.
Yeah, well, I'm considering bosonic system. Sorry.
Oh, okay, great. Okay.
Yeah, you could consider graded algebra, I believe. But then, yeah, I should maybe work on this seriously. This part should be worked out separately.
I see.
Yeah,
and one more maybe just clarifying question. So the so within this this patch construction of the picture you're just above were drawing, this where you have each patch has sort of topological order. So within this picture, you will always, is it true you will, I mean, so if the total manifold here was sphere, for example, suppose you put these patches on a sphere, so it will always have degeneration. I'm just confused about, so are we trying to say this picture is, are you ruling out this kind of, I mean, or is it unstable? I'm just trying to understand what is the, if I put these patches where each patch has some degeneracy on a sphere, so what is the statement that we don't consider this kind of systems? Right. They don't satisfy your condition. That's the statement I would, okay,
that's right.
That's mine.
My notion is precisely designed to rule this out from my consideration.
Right. That's mine. Okay, thank you.
Yeah. Sure. Okay. So let's.
Excuse me. Following Taron's question, maybe can you maybe predict, or can you say some words about the fermionic system? What are the difference? Just maybe as far as you can say. I didn't get what part need to be revised about your statement.
Well,
other than just formally a graded Z2 fermion parity algebra, what are the difference that I should expect?
Maybe we can look at the proof where the fermionic Z2 grading, if you have a Z2 grading, then usual commutativity should be replaced by the supercommutator, depending on the grading, right? And in that case, like what can change? Well, I mean, it fails from a very early stage. I'm going to use some information theoretic quantities like entropy, mutual entropy, continuity of the mutual information, and so on. And those are, well, yeah, I don't really know how to handle those in the overall Z2 graded algebras. Yeah.
But how will you affect the degeneracy bound?
I don't know. I suspect that the degeneracy bound will stay the same with a minor correction, like in the 1D chain versus that chain in 1D versus bosonic chain with non-degenerate graph state. I do not expect that the codimension 2 can be broken, but well, it's maybe it's my hope. Yeah, I should work on that. Thanks.
Thank you.
Yeah. So the proof is actually pretty simple. It quotes an old trick in the information theory from late 90s, applied in our topological setting, which will come later. So let me remind what the information theory argument is. Suppose you have some finite system. Dimension can be very large, but still finite. And we have a tripartition ABC of the degrees of freedom. And suppose the underlying state is entangled with some reference system. Yeah. Then suppose the system A, well, there's an underlying entangled state. And suppose A and the mutual information between A and R is bounded by some small number that depends on some small parameter delta. In the exact case, you can always set delta to 0 without worrying about this log dimensional factor. The log dimension pi in this case is pi. Pi is just dimension pi is just a dimension of the reference system. So we're considering a subspace in the composite system of three regions, and that subspace is somehow entangled with the reference system R, whose dimension is exactly my subspace and ABC side. Then this is an assumption. Well, we're considering my notion here. This is purely information theory consideration. Yeah, and in addition to that, suppose B is has a small mutual information with R, bounded by delta times the log dimension. Then a simple manipulation of, well, I can rewrite this inequality in this way. SA plus SR minus SAR, that's the mutual information, and we just assumed that quantity is smaller than this quantity, where K is the line log dimension. And if I assume that the entangled state itself is pure, then by symmetry of von Neumann entropy, the SAR is equal to SBC, because there are only 4 regions involved. And then I use just a subadditivity to upper bound this SBC as a SB plus SC. I do the same thing with the A replaced by B. So everything is symmetric between A and B. So I would immediately get an inequality. SB plus SR is at most the error term plus SA plus SC. If I sum the two inequalities together, then I can cancel, SA appears here and there, SB appears here and there. So 2SR and 2SC and 2 delta K. So we have this inequality, and after rearrangement, we get that. As long as delta is smaller than 1 here, this is some positive number between 0 and 1, and this K is my log dimension, and this is a bound. The C SC is bounded by the volume of C, right? The number of degrees of freedom, well, Hilbert space dimension, log of that, of system C. So we have this is completely general thing. I mean, well, as long as we have Q bits, not the fermions. There's no physics here yet. Now let's apply this inequality to sphere using my notion. So the sphere, by definition, looks like this. And there is a northern hemisphere that I call A, and there's a southern hemisphere that I call B. And both A and B separately, well, individually, A and B are topological balls. So my condition demands that A must be correctable on its own, B must be correctable on its own, and the correctability is equivalent to having a small mutual information with any other reference system. Yeah, the correctability of A is basically up to small correction delta. The mutual information is small. So I can apply this inequality, but where is C? I have divided sphere into 2 disks, A and B, and C is taken to be the empty set. The volume of the empty set is 0, so K must be 0. K was log of subspace dimension, therefore the dimension of the pi must be 1. Okay. Now let's go to surface. Let's consider the oriented case. Suppose I have genus 3 surface. what am I going to do? One surface, the one torus piece, can be divided in this way. Here I A, B, B. I'm going to divide my system in this way. So, so A is no more a contiguous set. They are separate, but A itself, A is like, disjoint union of form like this. The corners are cut out by C. Yeah, union of I, that's A. And union of B's, that's my C. And similarly for B. The key is that A is a disjoint union of ball-like region. Well, this looks like a ball, like a disk. And B, the same is for B. And C occupies a small number of dots. So I have engineered the tripartition in such a way that the volume of C has codimension 2. In this case, dimension 0. 4 dots. That's it. Of course, the length scale, the diameter of my one dot is order lattice spacing A. So even if I take a neighborhood of A still remains as a disjoint union of topological balls. So my condition was that, for whatever those regions are, as long as they're disjoint topological balls, they should be correctable. So I have the correctability on A as well as for B. So my degeneracy is bounded by the volume of C. But so for genus 1 case, it is bounded by C. But how can I handle those larger cases? Well, the trick is you prepare. I need more room. Yeah, let's do it here. What you do is you prepare this exactly the same copies of the genus 1 decomposition. If you make a small hole, you cut out a small disk from here, and then you connect the holes together. This is a construction of genus G surface. Yeah, you can consider this situation as like I have a polygon decomposition of the surface in G sheets, but you make a small, like a wormhole, like this. And my previous manipulation just goes through. You can subdivide these regions a little bit to make it into a disjoint union, still maintaining the fact that C occupies a small number of dots whose size is order of lattice spacing, and the number of such dot is proportional to your genus number. Nothing else. There's no metric involved. Well, metric involved only in the bound for the volume of C. So in the surface case, for the two-dimensional case, the log of Gradius degeneracy is going to be bounded by some function of genus. And we know from examples that this bound is tight. We know an example where Gradius degeneracy grows exponentially in the genus. And that's consistent with my, well, that's consistent with the conclusion from my condition. In the general case, the strategy is similar. We need a cellulation, D cell, that is colored either red and blue. In this case, this is two-dimensional cell that is colored, well, say this is red and that is blue. Yeah, I have color red and blue. That is colored red and blue. And each of them should be a ball. And if you delete the codimension 2 skeleton from one color, a collection of one color. So in the two-dimensional case, it'll be, oh yeah, here's another example. If you color, you can consider a three-dimensional torus with my cell relation like this. So these are my blue 3 cells. And if I delete a codimension 2 skeleton, codimension 2 skeleton is like is those lines, then it becomes the collection of all blue cells becomes disjoint union of balls. And how large should the codimension 2 thing should be? It needs to be thick as the lattice spacing A, order of A, and that's enough. So the question is, to handle the general manifold, how can we find a d-dimensional cell that is two colorable in such a way that the collection of one color minus d-2 skeleton, some small neighborhood of d-2 skeleton, is going to be a collection of balls? And for that matter, I can resort to the Whitney theorem that for any triangulation of your manifold, if you make a barycentric subdivision like that, then the sum of all codimension 1 cells, so in this case, the Z2 chain, that is this plus that plus everything, codimension 1 chain, that is going to be the representative of Poincare dual of Seyfert-Whitney class at degree 1. So they are an orientation domain. And the Whitney theorem says that the content of the Whitney theorem is that the sum of all codimension 1 cells is Z2 closed, and that is Poincare dual to the orientation class. So in particular, such a class is a boundary of these cells when the overall space is orientable. So so we collect, this boundary of sum if orientable. The W1, the upper one, because it's the codimension 1 cell chain, is boundary of some collection of D cells. And I color that as red. And you can work out that that decomposition satisfy my criteria. Those that are included in this chain is colored red, and those that are not included is colored blue. And the intersection of any 2 cells of the same color is through the codimension 2 skeleton. So that satisfied all my criteria. And my degeneracy bound log of dimension of pi is going to be the volume of the codimension 2 geometrical structure. So I get the general bound that just right. Oops. This is order of A D-2. In the non-orientable case, what you do is you barycentric subdivide twice. Then you have 2 representatives of the orientation class. And since there are both orientation class, their sum must be, again, non-homologous, and you do the same thing here. I believe, well, there could be other arguments, but I found this argument simple enough that I come to conclude. Yeah, so in the Fermioni case, well, we should work from this again. I'm not sure how it generalized to the Fermioni case. And all the other arguments are pretty geometric, so probably doesn't need any modification. Yeah. Last time I talked about a 10-minute talk of this paper. Someone in the audience asked me the following question, and I want to answer now. So the person in the audience asked me, "Oh, what if I consider? I mean, what do you call this homogeneous?" Here's a quote unquote counterexample. What if I consider a three-dimensional system that consists of sheets of two-dimensional independent systems, decoupled two-dimensional layers? Now, since we know that there are infinitely many two-dimensional theories, I could put anything on each sheet. And I consider the collection of those in my three-dimensional state. Well, and since each sheet obeys my condition, and there's no correlation between the sheets, it appears that my infinite stack of this completely unrelated states should obey my homogeneous condition. And this state looks inhomogeneous. Well, yeah, I appreciated the question, and it is a valid criticism, but there's a technical piece that actually rules out this example, that makes this into a non-example, and it has something in it, so I want to discuss. So basically, what I want to say is that if such a disjoint independent collection of sheets is going to be homogeneous under my definition, then I claim that there can only be finitely many choices in your sheets, finitely many choices of anyon theory that you can plug in to each sheet. You cannot have infinitely many different sheets. It actually comes from the two-dimensional bound. So let's recall log of dimension of this is smaller than genus. Well, there's a genus term, and there is the degrees of freedom density term. We did not have to discuss this one because it is so, so basic notion, but this enters when you convert the entropy of C into the volume of C. There's a proportionality constant here, and that depends on the degrees of freedom density. Now, what does that mean? I demand this quantity to be uniform across my system, and A is a fixed constant. So, in particular, if you fix your Hamiltonian's range, so this is completely independent discussion, only for 2D. Equals to. When you write your Hamiltonian like this, so A should be, well, A is like lattice spacing, but it should be larger than your correlation. It should be larger than your Hamiltonian range, at least. Otherwise, you would end up with a weird situation like we have covered last time. So the Hamiltonian term has a limited range. So one Hamiltonian term can act only on some bounded number of qubits because my degrees of freedom density is fixed. Then my bound says that, oh, on say torus, so the genus bound goes away, is absolutely bounded by these two quantities, regardless of details of any Hamiltonian. Interpretation is that as long as your Hamiltonian obeys my homogeneity condition, your ground state degeneracy has an absolute bound in terms of local density. So if your local degrees of freedom is say qubit and your Hamiltonian is acting on say 4 sites, then the resulting anyon theory that you can write has always a bounded rank. a constant rank. But the rigidity theorem in the modular tensor category says that given a rank, there are only finitely many anyon theories. So let me recap. For fixed local dimension and fixed range of your Hamiltonian terms, basically the number of anyon theories that you can write is bounded. In order to realize the infinite family of anyon theories, you have to gradually increase your interaction range a little bit. It will be slow, but you have to. So as long as you fix the degrees of the density and the constant coming in my homogeneous notion, you can't write down infinitely many different sheets here. So if you were to make this system homogeneous, then the only choice is that there are some finitely many, some constantly many different anyon theory, and you can plug that in for each sheet, but that's all you can do. So infinitely different stack of three-dimensional theory from a lower dimensional two-dimensional theory is not going to be homogeneous under my notion.
A question.
Yes.
Is it known how does the, for example, ground truth degeneracy or those any such data expands as you increase the range of interaction? How slowly it grows, or how with range of interaction? Is there any results?
Well, that depends on the, well, I don't actually recall the exact dependence. So we need information about the number of the modular tensor category given a rank. And we probably need some knowledge about how fast this function grows as a function of the rank. Probably exponentially at least, maybe faster.
Yeah, right.
Yeah.
Okay.
So yeah, the range grows very slowly.
Right. Sense.
Yeah, Juven?
Yes. So this example shown on the screen is not a homogeneous based on your definition and clarification. So even if it violates this degeneracy bounds, it's not an example. And I think earlier you also mentioned this topological defect networks, right? It's also a non-example, is that right?
No. So
topological defect network is non-example.
Topological defect network.
Yes.
Yeah, defect network. Well, it is a non-trivial condition for the topological defect network construction.
But is this homogeneous? I think earlier, if I didn't misheard here, it's homogeneous. So you can also keep the degeneracy bound. Okay, good.
Yeah,
I'm very good.
Depends.
Okay.
Yeah.
Okay.
When you construct.
Yes. Can you give the clarification when it will be homogeneous, when it will be not? Again, I think you mentioned that, but maybe I didn't understand the difference. Yeah. It's somewhere late, like few slides,
right?
Maybe later.
Well, in the network construction, you have a tunable parameter that is the intermediate length scale, small l, and depending on how you choose this length scale, you may end up with an inhomogeneous or homogeneous state. Certainly, if you chose this way, it looks like it's going to be inhomogeneous, but that again depends on how you glue them together. If you glue them sufficiently strongly, then it may have chance to become homogeneous under my definition. So I think, well, another extreme is that you may set this to be equal, like this. Then, all the network goes away and you are left with the one block, and that is also homogeneous. You can go to the other extreme. You can set like 100A to be your intermediate length scale and let the overall system size to be much larger than that. In that case, whether it is homogeneous or not depends on how you glue them.
Okay.
Yeah. So
But let me just make sure also the most example of the fractal lattice model in the literature also count as homogeneous
yes.
in your
Yes.
definition for the
Yes.
topological model.
Yeah.
That's fine. Thanks.
So I wish my notion is some minimal requirement for any uniform or homogeneous state. I think it's too strong to claim that my notion is going to be sufficient, but at least I think it's necessary to make sense. Of course, that's not a mathematics. It's just up to an opinion. But I think it's a reasonable starting point. Yeah. Oh, I have spoken for 1 hour and 15 minutes. I will, stop here, and thanks.
Thank you very much. Other questions from the audience? Feel free to speak up.
I have a question. Yeah, very nice talk. It's amazing. Yeah. So, if I take a system which is not within your discussion, let's say some gapless system, and assume some. This may be a speculative question. So if I assume some dependence of the mutual information on maybe some distance, like say it's power law or something, that's very common between some reservoir. Can you still obtain some interesting kind of bound on low temperature entropy or some or low lying density of states, or have you tried something? Because it's more about it's like if and if then statement. If I assume some form of some power law dependence, or does it completely doesn't get anything?
Let's see. Well, I can imagine that as you include some of the low-lying states in energy to your pi, the probing observable to distinguish those states may have gradually smaller and smaller support. That's possible. And so the correctability becomes weaker and weaker. Yeah, you may have some room for non-trivial result, but it's unclear. I mean, it may heavily depend on the well, you certainly use the approximate correctability criteria rather than the exact one. And
right.
Then it all depends on how the tail of the correctability plays with the number of states in the low energy window. Yeah, it's too difficult for me to make
right. No, it's not an easy question at all. Yeah. The reason I was asking was because there's this general result for CFT. Suppose you consider some CFT, then the entropy at low temperature has some interesting power law with dependence on the system size L, which is this Cardy's famous formula, Cardy density of states, and it's some L to the power some function of D, which is different function, of course, than your function. I was wondering, is there some way to think about that using some approximate error correction? Right, at least in the case of in ADS-CFT, people always say that the low energy subspace is an error correcting code, as you might have heard of it. This work by Pascal, Benny, and various people on the at the
Yeah.
and there it's not a gap, it's not a topologically ordered system, it's more like it's just a CFT, but it's still there's still some notion of error correction because you can move operators around, like action of operator in one part can be moved around to another region and so on, despite it not being a gapped system. So I was wondering, in those systems, is there some constraints and so on? Yeah.
Oh, well, yeah. Sounds interesting. Right. Well, in that context, maybe precise bound is less of an interest rather than an interesting consequence, even if it's heuristic. Yeah. The place where the approximation, the parameter creeps in is in the continuity of the mutual information. So correctability can be phrased as a approximate a product structure of the underlying reduced density matrix with the reference system. And from that information, you convert it into entropy bound. And that step is pretty, well, that step alone is pretty tight, but yeah, it's very speculative, but yeah, it sounds very interesting.
I have one more question. I don't know, maybe there are other questions. Can I ask?
Please go ahead.
So when you have some finite temperature topological order, let's say 4-iteratory code, how does one think about the same condition? Do you have to? Is it still in terms of mutual? Because then the entropy is not a good, at least generally the 1-over entropy is not a good measure of entanglement. Do you replace it with some mixed state entanglement measure, similar condition? When
well, I'm not sure. Yeah, I get that. When you think about the thermal states, then there is a thermal entropy that creeps in whenever you take a entropy formula. And at this stage, the use of entropy in these arguments is more of a tool rather than some fundamental link. It was just a convenient thing to use the symmetric property and the subadditivity. And the fact that it relates the volume of a certain region with the dimension.
Yeah, that's true. But the question is whether it's true or not, in the sense that it may not. Maybe the error correction condition is a bit different when you're in a mixed state, right? It's not obvious that it is exactly the same condition, even, or at least not the most natural condition to impose, because we are kind of polluting with some classical stuff. And
yeah, I'm not sure. But if you want to prove certain degeneracy bound, then my technique will be probably very loose. So it is tight in the sense that, well, there are saturating samples, but if you go to like a three-dimensional topological order in the conventional sense, then this bound gives log degeneracy to be linear in linear dimension, whereas the true ground state degeneracy is just a constant that depends on only on topology, and the gap just becomes worse if you go to higher dimensions.
No, but don't the fractons have saturated bound e to the power L in 3 dimensions?
Yeah, it does. But what I'm saying is, the self-correction requires you to go probably one more dimension down than codimension 2. So
okay, I understand. Okay,
yeah.
thank you.
Actually, do you mind to explain simple things? Just the non-example you show for this, I suppose, is also a non-example from a DeFi network. Can you just say again? You probably already did, but can you explain again how this become non-example? Sorry for asking this. Yeah, please.
So in this non-example, the key is that you have intermediate length scale L that has nothing, well, basically nothing to do with the global size. And my notion has only two length scales, the lattice spacing and the global diameter. That's it. So if there's anything that sits in between, then it's now destined to become a non-example.
But a lot of topological DeFi networks, you say, has this intermediate little L scale, right? But
Yes.
you also say they can be examples. So I just want to hear the clarification: when and when cannot. When will they be example and when will they be non-examples?
I would be wrong to make a sweeping statement here. It really depends on how you glue the small blocks. I mean, so even if you start with, well, you can construct the cubic model starting with a network construction. There, the intermediate length scale is tied to the lattice spacing side. And the gluing was strong enough that you could guarantee that you satisfy the homogeneity, my homogeneity. Yeah, that's one data point. And in this non-example that you see in the screen, that's just completely decoupled blocks, rather extreme case. And
yes. Mm-hmm. Yeah. I get your point, but is it possible to make this statement more mathematical? Like in terms of a DeFi network construction, when will you get homogeneous?
No,
when would you get non-homogeneous?
That is an
Is there some way
question.
to? Yes. Yeah. How is it possible to make it sharper? Like how is the gluing process? Yeah. What's the data? Okay.
Right.
That's what I want to ask.
Right. That's precisely the research question I am posing. Here is a reasonable condition I propose, and it is desirable to find a some condition under which the topological DeFi network becomes homogeneous.
Yes. Mm-hmm. Yeah. Okay. But do you have a second thought on answering this question? In terms of what should be the data to describe the gluing? Maybe, I don't know, is there some yes, as you said, the range of interaction, also possible some maybe entanglement structure around different sites? I don't know exactly, but I'm just don't know what you have in mind. Yeah.
Well, it must be some some condition when you introduce the gap boundary between two blocks, the transparent one, or condensing some subparticles in there. I believe there is some algebraic condition you can impose. You should condense this much, for example. If you didn't do it that strong enough, then there's a I don't really know.
Thanks. Let's think about this. Thank you. Okay. If no more questions, then let us thank Jeongwan again. Thank you very much for the great talk. Thank you.
Thank you.
Thanks. I'll send you the recording. Thanks. Bye-bye.